All right, this video is going to go over the sound and light review. So we're going to start on number one. What type of wave is a sound wave? It is going to be longitudinal, which basically means it just compresses back and forth, side to side. So you could say, or it is a compression wave as well. Either one is acceptable. Okay, so your EMR waves, those are transverse. So like radio light, transverse looks like this. Okay, and your compressional looks like basically when it stretches out and then starts tightening up and compressing and then stretches back out. Okay, what is the source of energy for all sound waves? Okay, you need a vibration. Okay, so basically how we talk is we are emitting air from our diaphragm and our vocal cords constrict and relax and stuff, and they cause vibrations in that sound, and that's what you're hearing. Number three, what wave property is responsible for pitch and loudness? So pitch is frequency. Okay, so that'll determine how high it is, how low it is. Okay, as far as pitch goes, it's not really a loudness. And then loudness would be amplitude. Okay, so explain resonance. Okay, so resonance is when a frequency matches up with the natural frequency of an object and increases the amplitude. Okay, so like opera singer and glass is what happens is when the opera singer starts singing, that glass will start vibrating in its own natural frequency. Now, if she can match that frequency perfectly, so that means her frequency coming out of her mouth is the same frequency that glass is vibrating at. Okay, if those match up, that means they'll meet up and the amplitude will increase. And if it's too much, then the glass breaks. That's how that works. Number five was the speed of sound at negative 14.5 degrees Celsius. So remember we have this equation right here. V equals 331.5 plus 0.6 times whatever the temperature is. So in this case, negative 14.5. Okay, put that in a calculator. And just watch out for the negative. Make sure you keep that in there. So you're going to get 322.8 meters per second. Okay, Doppler shift. Okay, that is when a sound wave bunches up in front of a moving object. So let's say you have an object that is moving this way. So what's going to happen is these sound waves are going to start bunching up in front of it, which is going to create a higher pitch. And the sound waves behind it are going to stretch out, which is going to make a lower pitch. Okay, so that is Doppler shift. It's just basically the bunching up of waves to make a high frequency in the front, and then the stretching out of waves to make a low frequency in the back. Number seven, what is the Mach number? What is the speed of an aircraft at Mach 2.5? So Mach is the speed of sound at a certain temperature. Okay, so at 0 degrees, so at 0 degrees Celsius, okay, you could go right up here and use that same equation here, and you would get basically 332 meters per second. Now, if we gave you a certain temperature, so let's say what is Mach at 5 degrees Celsius, then you'd have to use that equation again, figure out what is my speed of sound at that temperature, because that is your new speed of sound. Okay, for now, we're just using the 0 degrees Celsius one. So if I'm going Mach 2.5, I'm going to multiply that by 2.5, because Mach 1 is the speed of sound. So you're going 2.5 Mach, that means you're going 2.5 times the speed of sound. So you get 830 meters per second. Number 8, at a height of 10 meters above the surface of a lake, a sound pulse is generated. The echo from the bottom of the lake returns to the point of origin 0.14 seconds later. The speed of sound in air is 343 meters per second, and the speed of sound in water is 1,482 meters per second. How deep is the lake? Now, on the test, more than likely, you'll see just a basic echo problem. This one's actually more complicated. I'll show you how to do it, but I'm not going to throw in different mediums. So what basically happens is you have 10 meters down until you hit the water, so that's 10. Then you've got to go to the bottom of that water or that lake, and you've got to go back up to the surface, and we don't know what that distance is. And then you got to go another 10 meters back up to where it came from. So I have a total time of 0.140 seconds. So I'm going to do first is I'm going to figure out how much of that time was it spent in air. Okay, because I know my velocity. So V equals D over T. My velocity is 343 equals D, which is 20 meters. And then time, I don't know. So just swap the 343 and the time, and you get a time of 0.58 seconds. So that's how long it was in the air. So what I'm going to do is I'm going to subtract it from that total time. So 0.140 minus 0.058. Okay, and that is going to give you 0.082 seconds in water. Okay, so that is the time to go down and the time to go back. But remember, we only care about how deep it is. We don't care about how deep it is to go there and back. So all I'm going to do is I'm going to split this in half. Okay, and that gives you a time of 0.041 seconds. So that's how much time it takes to get to the bottom of that water. And now you're just going to do V equals D over T again. So 1482 is your new V. Distance you don't know. And then your time is 0.041. So multiply those, and you get a distance of 60.76 meters. Okay, so again, on the test, more than likely you'll just see a basic echo problem where you just need to make sure you are cutting the time in half to figure out how far that surface is. So don't get too hung up on this one. 9 lists 3 applications of sound waves in medical devices. So I'm not really too worried about this. This is just mostly so how you can see this is actually used in real life. Okay, so stethoscopes are the things that you see doctors wearing around their neck so they can hear your chest. Okay, then you have ultrasound. So one day if you need an ultrasound done, okay, so that's how they take images of the internal body or maybe a baby, things like that is through ultrasound. And then something like a hearing aid. Okay, so there's just multiple things that are actually used with this type of science. 10, what is the average range of human hearing? So we hear about 20 to 20,000 hertz. Okay, so anything above 20,000 would be considered ultrasonic, and then anything below 20 would be infrasonic. Okay, so let's move on to the next one. So what is the sound barrier? That is the speed of sound at that temperature. Okay, so speed of sound at that temperature. Okay, so breaking through that sound barrier is, so what happens is a sound barrier is basically a pocket of dense air that's in front of that plane where those waves are basically that air is condensing up, okay, because you're basically getting to how fast that sound actually travels. And then once you break through that, that's when you hear the big boom. Okay, that's breaking the sound barrier. 12, how many times the intensity is 70 decibels than 30? Okay, so there's 2 ways you can do this. One, you can do it this way, 30 to 40 to 50 to 60 to 70. Okay, so don't do 10. So you start off with 10 between the 30 and 40. Don't start it under the 30 because that's how you get people doing too much. Okay, so they do 10 under 30, then 10 under the 40, and then they have one more than they needed it to. So from 30 to 40, it's 10 times. 30 to 50, that's 100 times. 30 to 60, that's 1,000 times. And then 30 to 70, that is 10,000 times. So that is one way. Okay, the other way is if you start at 30, how many times did you go up by 10? You went up by 10 4 times. So you could literally say 1 times 10 to the 4th times. Either way works. 13, how many decibels louder is 90 than 50? So 50, 60, 70, 80, 90. So 10 times, 100 times, 1,000 times, and 10,000 times again. Let's see, what is an echo? So an echo basically is when a sound wave is reflected off a smooth and hard surface. So when a sound wave is reflected off a smooth and hard surface. Okay, why does sound waves travel faster in warm air, and why does sound travel even faster in liquid and solid? Okay, so if temperature goes up, okay, what happens is those particles start moving even faster, so that means kinetic energy goes up as well. And if your whole goal is to transfer energy, okay, it wouldn't do very good to have particles that are already moving slow. You'd rather them already moving fast. So that means the velocity goes up since that kinetic energy is up as well. Now, as far as sound goes, okay, sound will prefer a solid or a liquid. Okay, so the more dense, the better. Okay, so again, sound is basically like a relay race. If you have a solid, those particles are right there. Those are available. Okay, so it's easy to hand off the energy really quick. Versus like in a gas, those particles are actually a distance away, so the particle's got to get there, then hand it off, and then get to another one, then hand it off. So that's why sound prefers a more dense material. It goes a lot faster and more dense and a lot slower in a gas. Number 16, what happens if you force something to vibrate at its natural frequency? So we talked about that already. That's when resonance will occur. 17, sound travels at the speed of 343 meters per second at 20 degrees Celsius. The wavelength of the wave is 1.31. Find the period of the wave. So we have our equation V equals wavelength over T. Okay, so we're just going to plug in. So V is 343. Wavelength is 1.31. And then T is right there. Now, could you have done this another way and stuff? There's always different ways to do this and stuff, but this is probably the quickest way. Okay, so I'm going to switch those two. So 1.31 divided by 343, and I get a period of 0.0038 seconds. Okay, so here we have on number 18, this is actually an example of Doppler shift, okay, or Doppler effect. So when an automobile moves towards a listener, the sound of its horn seems relatively high-pitched. Okay, so that frequency is really high right here. Okay, so that's responsible for pitch. And then when it moves away from you, you can see that the frequency of the waves is a lot lower, so that's going to make a lower pitch. Now light. Okay, so light is a small range. Small range of frequencies of electromagnetic waves, so EM waves, that are visible. Okay, and all of these are going to be traveling at the speed of light, so 3.0 times 10 to the 8th. Okay, what is polarization of light? So that is when, so EM waves are in all directions. So electromagnetic waves, remember, they look like this. Now, it's not just always on one plane. They're in all, it's like basically 360 degrees of different planes. So what happens is when you have polarized sunglasses, it only allows one direction in. It blocks out all the others, which limits the light on your eyes or anything, which actually reduces that damage. Okay, so EM waves can only be allowed in one direction. So EM waves are only allowed in one direction. Now, what is a light year? So a light year is the distance light travels in 1 year. So distance light travels in 1 year. So it's not a time, it's actually how far light just travels in that time. So if you do D equals V times T, so your V would be the speed of light, so 3.0 times 10 to the 8th. Now, 1 year doesn't really do me good, so there's 365 days in 1 year, and there's 24 hours in 1 day. There's 60 minutes in 1 hour, and then there's 60 seconds in 1 minute. So you get a value of 9.46 times 10 to the 15th meters. So that is how far it travels in 1 year. So state the law of reflection. Basically, this means is your angle of incidence. That means the incoming angle is always going to be equal to the angle that is reflected. Okay, so if you have a surface right here, here's your normal line. If you have something coming in, what it's going to do is it's going to reflect off, and these two angles are going to be the same. Okay, so that's basically all the law of reflection states. Just pay attention to that and make sure if I ask for reflection, it's the same angle. If you ask about refracted angle, that's when we do the whole Snell's law thing, which we'll do here in a bit. This one, do not worry about regular or diffuse reflection. 24, define refraction. Okay, so that is bending of light when entering new medium. Okay, so there's a few things that are going to change and one thing stays constant. So frequency is constant. Okay, but wavelength, okay, our speed and direction all change. Okay, so normally if you were staying in the same medium, if frequency goes up, wavelength has to go down, because if you're in the same medium, velocity doesn't change. But as soon as you enter a new medium, those rules kind of go out the window. Okay, your frequency is just dependent upon the source. Okay, so basically what's sending it at that frequency, but as soon as it hits a new medium, its wavelength will change, its speed will change, and the direction of the wave will change as well. So our Snell's law, so we start finding refractive angles, so it's Ni. So Ni is your refractive index of the incident medium. Okay, so that's basically how dense the original medium was. Okay, times the sine of your incoming angle, so your incident angle. And then Nr is basically how dense is the new medium that you're traveling into, times the sine of your new angle that you're having in that new medium. So number 26. So a ray of light traveling through air, 1.003, has an angle of incidence 41 degrees. Okay, upon a sheet of crown glass at endpoint 1.52, what is the angle of refraction? So if I draw this, so here is my normal. Okay, so here's my incident. Okay, so it comes in at 41 degrees. Okay, my index of refraction is 1.003 here. And I'm going into crown glass, which is 1.52. Now, I know going from less dense to more dense, this angle is going to get smaller. It's going to go towards that normal line. So that means we are looking for my refracted angle. So I'm going to do Ni, so which is 1.003 times sine of 41, my bad, equals Nr, which is 1.52. Sine of theta r. Now again, make sure you're in degree mode. So what I would do is I would solve the whole left side and then divide it by 1.52 and then take the inverse sine, okay, of that. So whenever you're bringing this sine over to get it off, just make sure you do inverse sine and you should get an angle of a refracted angle of 25.59 degrees. Okay, what is the index of refraction for a material in which light has a velocity of 2.19 times 10 to the 8th meters per second? So this is that equation N equals C over V. So C is basically 3.0 times 10 to the 8th. That is the perfect scenario for light. Okay, that is as fast as it goes. So 3.0 times 10 to the 8th. And then velocity on bottom is basically how well light travels in that new medium. So 2.19 times 10 to the 8th. So apparently we can definitely see that it is not traveling as fast. So I'm going to divide those and you get a refractive index of 1.37. So basically the higher that number, the more dense the material is, which slows down light. Let's see, 28. What is total internal reflection? Okay, so when you go from more dense to less dense, okay, your refracted angle gets bigger. Okay, so if you switched over there, your refracted angle gets bigger and it basically has, or it maxes out at 90 degrees. So if I were to look up here, let me change my color real quick. At this example up here, okay, so if I was going from more dense to less dense, this angle can get bigger. Okay, so that means I can only move this incident angle down so far before it reaches its max refraction, and then it just all becomes reflected. Okay, so if I drew a medium, and here's my normal line, okay, let's say this was my critical angle. So say this is as far as you can go where you still have refraction, but it's going to be at 90 degrees. Now what I did is if I come in at this angle, which is a lot further past the critical angle, that means none of it's going to go through to the new medium on bottom. So nothing goes down here, and it only reflects back. Okay, so there is no refraction, it only reflects. Let's see, 29, what is the critical angle when light is going from crown glass to air? Okay, so if you actually look at that box that's on the back of your packet, okay, what we can do is we're going to use our equation. Let me switch colors real quick. Critical angle is inverse sine of Nr over Ni. Okay, Ni is always the one you come in at. Okay, so you're going from crown glass to air, so that means Ni is crown glass, and then air is your Nr. Okay, so if you look on that box on the back of your periodic table, I'm sorry, not your periodic table, on the back of your packet, okay, Nr is air, which is 1.0003, and then Ni is your crown glass, okay, which is 1.52. Okay, make sure you're in degree mode, and you get a critical angle of 41.59 0.15 degrees. So that's the max angle you can come in at where you still have refraction. Anything past that is going to be total internal reflection. So speaking of it, I don't know why that keeps happening. List 2 applications of total internal reflection. So fiber optic cables work this way. Okay, you don't really want to lose light. So basically it's all internal reflection. And then things like endoscopes, so a lot of cameras and stuff will do that, where you want basically everything to stay where it's at and not refract through. 31, what is the dispersion of light? So dispersion of light is a separation of light into its spectrum of colors. So basically how rainbows work, okay, it's going to split off into its Roy G. Biv, okay, because it hits a new medium. Each color bends at its own wavelength, okay, and then that's what causes it to separate. Okay, and that's how you get dispersion of light. 32, what is the frequency of an X-ray with a wavelength of 0.5 nanometers? So again, watch out for that nano right there. So if you use that metric scale on the very last page, nano is times 10 to the negative 9. So we're going to do 0.5 times 10 to the negative 9, and that'll fix it. So we're looking for frequency. We're talking about an X-ray, so that means we're talking about EMR wave. Okay, so that means we're dealing with speed of light. So C equals frequency times wavelength. So 3.0 times 10 to the 8th equals frequency. We don't know. Wavelength is 0.5 times 10 to the negative 9. Please make sure you use parentheses, otherwise you may get a wrong answer even though you had everything right. So you get a frequency of 6 times 10 to the 17th hertz. 3, what is the wavelength of a microwave whose frequency is 2.4 gigahertz? Okay, if you look up gigahertz, okay, so giga is 10 to the 9th. So this is 2.4 times 10 to the 9th hertz now. Okay, we're doing the microwave, so still speed of light. So we're going to do the same thing. So 3.0 times 10 to the 8th equals frequency, which is 2.4 times 10 to the 9th. And wavelength, I don't know. So my wavelength is going to be, once you divide those, you get 0.125 meters. Okay, 34. Okay, so how does a ray of light change when it goes into a denser medium? Okay, so if I draw my barrier there, and let's draw my normal line. Okay, so this is my incident ray coming in. So this is my incident. Here's my incident angle. Okay, you're going to have some that reflects off. Okay, and that angle is going to, even though it doesn't look like it, these two angles are the same. That's your reflected ray. And we're going from less dense to more. So when you go from less dense to more, remember it makes it harder. Okay, so what's going to happen is that refracted ray is going to be pulled a lot closer to this normal. Okay, so that angle is going to be smaller. So here is your refracted angle, and here is your refracted ray. So basically your incident angle is going to be bigger than your refracted angle now. Okay, so when you go from less dense to more dense, okay, it's going to slow down. Okay, and that angle is going to bend towards the normal. Okay, so let's do the next one. So how does it look if we go from more dense into less dense? So let's do my barrier. Okay, let's draw the normal line. Okay, we're going from more to less. So incident rays coming in, incident angle. You have the ray that's reflected off, so there's your reflected. Those angles are both the same. Now, when you go from more dense to less dense, it gets easier. So the way I think about it is that ray basically just takes off. Okay, so it goes away from the normal. And so now your refracted angle is a lot bigger. Okay, so refracted angle is now bigger than your original incident angle. Okay, it's going to speed up. And it bends away from the normal. That'll end that one.